In this lesson, we will discuss maximal and prime ideals. So we begin by discussing an important class of ideals which are not contained in any other proper ideal. We say an ideal M of an arbitrary ring R is called a maximal ideal if M is a proper ideal, so M does not equal R, and the only ideals containing M are M itself and the ring R. So there are no other ideals in between M and R. So let's look at a quick example in the ring of integers mod 12. So in the set of integers mod 12, we have the following lattice of ideals. So in this lattice of ideals, we see that the ideals generated by 2 and the ideal generated by 3 are the only maximal ideals. Now, in general, not all rings have to have a maximal ideal. Not all rings have a maximal ideal. So, for example, the zero ring consisting of only the number 0, this has no maximal ideals. Because any ideal of the zero ring would be equal to the zero ring. Now for a less trivial example, let's look at the set of integers again. So for a prime P, the ideal generated by P is a maximal ideal. So let's see why. So let's suppose that the ideal generated by P is contained in some other ideal I, which is also contained in a set of integers. Then we're going to show that I will have to be equal to the set of integers. Well, if I does not equal the ideal generated by P, then there's an element in I that's not in P. Then there exists an integer n that's in I, but not in the ideal generated by P. Well, if it's not in the ideal generated by P, then it's not a multiple of P. So then P does not divide n And since p is prime, that means that the greatest common divisor of p and n must be 1. Well, if the greatest common divisor is 1, then I can find a integer linear combination of n and p that equals 1. So that is, there exists integers a and b such that an plus b times p equals 1. But now n is an element of the ideal I, and so is p. So since n is in the ideal, then an is in the ideal I, and similarly p is in I. So since n and p are elements of the ideal I, 1, which is the sum of two elements in the ideal, this must be in I as well. But since the ideal I contains a unit, the unit 1, so since I contains a unit, I must equal the whole ring, which is the integers. So we've just shown that any ideal that contains the ideal generated by p must be equal to the set of integers, and therefore this ideal generated by p must be a maximal ideal. So in the set of integers, any ideal generated by a prime number is a maximal ideal. Now we'll look at another example of a maximal ideal. We're going to prove that the ideal generated by 2 and x is a maximal ideal in the set of polynomials with integer coefficients in this ring. So we've seen this example of this ideal before, and we recognize this ideal as the set of all polynomials with integer coefficients such that the constant term is even. So now let's let I be another ideal containing this ideal generated by 2 and x. So let I be an ideal in this ring containing the ideal generated by 2 and x. So if I does not equal the ideal generated by 2 and x, then there must be a polynomial that's in I and not in the ideal generated by 2 and x. So then there exists a polynomial p of x that's in the difference I minus the ideal generated by 2 and x. So if p of x is not in this given ideal, then it must have an odd constant term. So then p of x has an odd constant term. And so just like in the last example, we're going to use this fact to show that I contains a unit and is therefore equal to the whole ring. So then we can write p of x equal to p0, which must be an odd number, plus p1x up to some nth term, so pn x to the n, where the constant term p0 is an odd integer. Now, if I take off the constant term, every other term of p of x is a multiple of x. So we see that since the ideal generated by x is contained in the ideal generated by 2nx, which is also an I, we see that the polynomial p of x, if I take off all but the constant term, this is going to be an element of I. So we see that p1x plus p2x squared plus up to pn x to the n, this polynomial is in the ideal I. But then the difference of any two elements of I is also an I. Then I can write p0 as the difference of two elements of I. This is p of x minus the polynomial p1x plus p2x squared all the way up to plus pn x to the n. So we see that p0 is an element of I. Now that p0 is an I, let's look at p0 minus 1. This is an even integer, and hence is an element of the ideal generated by 2, the set of all even integers. That's contained in the set of polynomials with even constant term, which again is contained in I. So we see that p0 minus 1 is also contained in I. So we see that p0 and p0 minus 1 are in I, so their difference is also in I. But I can write 1 as p0 minus p0 minus 1. And just in the previous example, we see that I contains the unit 1. So since I contains a unit, I equals the whole ring of polynomials with integer coefficients. So therefore, if any ideal contains the ideal generated by 2 and x, it has to be equal to the whole ring. Therefore, this ideal is maximal. So thus the ideal generated by 2 and x is maximal. The next theorem we prove is useful for determining whether an ideal is maximal. And this actually uses quotient rings. So we're going to assume that R is a commutative ring with identity. The ideal M is maximal in R if and only if the factor ring R mod M is a field. So to determine if an ideal is maximal, we can actually look at the structure of the factor ring R mod M. So let's begin the proof. So for the forward implication, let's suppose that M is a maximal ideal. Then, since it's an ideal and R is commutative, R mod M is also a commutative ring with identity. So now let's look at an element S, which is in R minus M. So it's an element of the ring R that's not in the ideal M. So we're going to look at the coset S plus M and show that S plus M has a multiplicative inverse. So then we need to show that S plus M has a multiplicative inverse in R mod M. So that will show that every non-zero element of R mod M has multiplicative inverse, and therefore R mod M is a field. So to this end, let's consider the set I which I'm going to define as the set of elements of the form RS plus M, such that R is the element of the ring R, and M is an element of the maximal ideal M. Then I claim that I is an ideal of R that properly contains M. So I is an ideal of R that properly contains M. So let's look at the proof of the claim. So to show it's an ideal, we'll first show it's not empty. So it's 0 can be written as 0 times S plus 0. And so this is an element of I. So I is not empty. Secondly, we're going to show that I is closed under subtraction. So suppose I have two elements of I. Let's write them as R1 S plus M1. And I subtract an element R2 S plus M2. Then, using the fact that R is commutative and has the distributive properties, we can write this as R1 minus R2 times S plus the quantity M1 minus M2. Well, since R is a ring, R1 minus R2 is an R, and since M is an ideal, which is a ring, M1 minus M2 is also an element of M, so this whole quantity is an element of I. So we see that I is closed under subtraction. Thirdly, let's look at arbitrary multiplication in the ring. So let T be an arbitrary element of the ring. So for all elements T in the ring, T times an element of I, so RS plus M. Then I can distribute the T and write this as TRS S plus Tm. So Tr is still an element of the ring. So if I put this in parentheses, think of this as Tr times S, and then Tm is also an element of M because M is an ideal and T is an arbitrary element of the ring. So this is still an element of the ring I. So we see that I is an ideal of R, and now we need to show that it properly contains M. So now any element M in the maximal ideal M can be written as 0 times S plus M. So it's therefore an element of the ideal I. So this shows that the maximal ideal M is contained in I, but recall that S is not in M, but S is contained in the ideal I. So S equals 1 times S plus 0. So this is an element of I, and S is not an element of M. So thus M is properly contained in I. So it's not equal to, it's contained but not equal to I. So this finishes the proof of the claim. Now back to the proof of this theorem. So since M is properly contained in the ideal I, and M is maximal, this means that I must equal R. So we have I equals the ring R. So R is a ring with identity, so now the ring I must contain the identity 1 as well. So thus 1 is an element of I, but remember every element of I looks like RS plus M, so when we can write 1 as some element R0 times S plus some element M0, for some element R0 of the ring and M0 in M. Now recall what we're trying to show. We're trying to show that the coset S plus M is a unit. So the coset 1 plus M is equal to the coset R0S plus M0 plus M. But since M0 is an element of M, it's absorbed by the capital M. So this equals R0S plus capital M. But then I can write this as a product of two cosets, the product of R0 plus M times S plus M. So this shows that S plus M is a unit in the factor ring R mod M. So thus, S plus M is a unit, and since it was an arbitrary non-zero element, we know that the factor ring R mod M is a field. So that proves the forward implication. Now we need to show that if R mod M is a field, then M is a maximal ideal. So let's suppose R mod M is a field, and let's let I be an ideal of R that properly contains M. So I be an ideal of R that properly contains M. And suppose we have an element S that's an element of I, but not an element of M. Now, that means that the coset S plus M is a non-zero element in the factor ring, because S is not in M. So this is a non-zero element. Of R mod M. And we're assuming that R mod M is a field, so therefore S plus M has a multiplicative inverse. So hence, there exists an element R plus M in the factor ring such that S plus M times R plus M is equal to the identity in the factor ring 1 plus M. So again, where 1 plus M is the multiplicative identity in R mod M. Now we're assuming that S is in I. So since S is in I, we have S times R as an element of I, because I is an ideal. But then I can write the coset 1 plus M as S plus M times R plus M, but by definition of multiplication of cosets, we have SR plus M, and therefore 1 minus SR plus M, this coset must be equal to 0 plus M, which is just equal to M. So thus 1 minus SR is in M, and which, remember, is properly contained in the ideal I. Then the element 1 can be written as 1 minus SR, which is an element of I, plus SR, which is an element of I. So this sum is an I. And therefore we can conclude that I is equal to R, since I contains a unit. So we've just shown that any ideal of R that properly contains M must be equal to R. Thus, M is maximal, and this concludes the proof of the theorem. So let's look at a quick example using this theorem that we just proved. Recall previously that we showed that the ring of polynomials with real coefficients mod the ideal generated by the polynomial x squared plus 1, we showed that this is structurally identical to the field of complex numbers. So by the previous theorem, the ideal generated by x squared plus 1 is maximal, because the factor ring is a field. Now we begin our study of another class of ideals called prime ideals, which extends the idea of a prime number into ring theory. Let's begin with the definition of a prime ideal. So R is a commutative ring then an ideal, let's call it P of R, is called a prime ideal if P, first of all, has to be a proper ideal, so P does not equal R, and whenever a product A times B of two elements in the ring whenever this product is in P, then A is in P or B is in P. So whenever a product is in this ideal, then one of the two factors, at least one of the two factors, has to be in the prime ideal as well. So let's look at an example of prime ideals. Let's look at the ring of integers. So let n be a non-negative integer. Let's look at the ideal generated by n. So then the ideal nz is a prime ideal in Z, provided that, first of all, n cannot equal 1, because then the ideal nz would just be equal to z. So we need n to be not equal to 1 so that the ideal is a proper ideal. And if it's going to be prime, then every time we have a product AB in this ideal, we need to have at least one of the integers A, B must be in the ideal NZ. So that is, if n divides the product AB, that's the same as saying that AB is in the ideal generated by n, then n divides A or n divides B. But if you think of this, we have a non-negative integer that's not equal to 1, and anytime it divides a product, it divides one of the factors. This is actually equivalent to the usual definition that n is a prime number. So this is equivalent to the usual definition that n is a prime number. So we see that the ideals generated by prime numbers are actually prime ideals in the ring of integers. Also, note that the zero ideal is also a prime ideal. Because the set of integers is an integral domain. So if AB is in the ring, the zero ring, that means that AB equals 0, which implies that A equals 0 or B equals 0. And that's the same as saying that A is in the zero ideal or B is in the zero ideal. So the prime ideals of the integers are just the ideals generated by a prime P and the zero ideal. So the prime ideals of the ring of integers are the zero ideal and PZ, where P is prime. And for another example of prime ideals, let's look at the polynomials with integer coefficients. The ideal generated by x is prime. So to show this directly, let's look at a product, a of x times b of x, and suppose this is in the ideal generated by x. Then ax times bx equals x times some polynomial q of x. Then let's plug in 0 into this previous equation. So then a of 0 times b of 0 equals 0 times q of 0, which equals 0. Now this is an equation involving only integers. So this product occurs in the set of integers, z, but since the ring of integers is an integral domain, and we have a product equal to 0, we must have a of 0 equals 0 or b of 0 equals 0. But that means that x divides a of x or x divides b of x. And hence a of x is in the ideal generated by x, or b of x is in the ideal generated by x. So this shows that the ideal generated by x is prime. Now, in the same ring, let's look at an example of a ring, an ideal that's not prime. The ideal generated by x squared is not prime. So this is the ideal of polynomials that are multiples of x squared. So to show this is not prime, just note that x is not in the ideal generated by x squared. So x is not a polynomial that's a multiple of x squared, but the product x times x, which is x squared, is an element of the ideal generated by x squared. So we have a product that's in the ideal such that none of the factors is in the ideal. So therefore this ideal is not prime. Now just like we had a theorem to show that an ideal was maximal using a factor ring, we're going to prove a similar theorem that can be used to determine whether an ideal is prime or not. So let's assume R is commutative. And the ideal P is a prime ideal in the ring R if and only if the factor ring R mod P is an integral domain. So the proof is not as involved as the previous theorem, and actually the proof consists of merely translating the definition of a prime ideal into the language of factor rings. So recall that P is prime by definition if and only if P does not equal R, and whenever a product AB is in P, then either A is in P or B is in P. Well, note that an element R is in P if and only if the coset R plus P is actually equal to 0 plus P in the factor ring R mod P. So let's now reinterpret the definition of prime using this fact. Thus, the ideal P is prime if and only if P does not equal R, and whenever A plus P times B plus P, which equals AB plus P, whenever this equals 0 in the factor ring, then A plus P equals 0 plus P, or B plus P equals 0 plus P. But that's the same as saying that R mod P is an integral domain. That means R mod P is an integral domain. That is, it has no zero divisors. So whenever a product equals 0, then one of the two factors has to equal 0. So I see that an ideal P is prime in R if and only if R mod P is an integral domain. Now let's put those two theorems together. Recall that every field is also an integral domain. So we have the following corollary. Assume R is commutative. Then every maximal ideal of R is a prime ideal. So if M is maximal, then we know that R mod M is a field. And since every field is an integral domain, we conclude that R mod M is an integral domain. And by the previous theorem, M is prime. So we see that in any commutative ring R, every maximal ideal is prime, but the converse is not true. There are prime ideals that are not maximal. So let's look at a couple quick examples. So as we saw in the ring of integers, for prime P, the ideal generated by P is both a maximal ideal of Z and a prime ideal of Z. Now the zero ideal containing only 0, this we showed is a prime ideal of the integers, but is clearly not maximal. Another example, the ring of polynomials with integer coefficients, mod the ideal generated by X is isomorphic to the ring of integers, which is an integral domain, so the previous theorem again shows that the ideal generated by X is a prime ideal. Recall we already showed this more directly.